Welcome to Module 45 in this series of lectures on statistical quality assurance and statistical process improvement. This is the third lecture on the analysis of so-called two-way factorial data. And in particular, in this module, we're going to talk about adding some notion of margin of error to the fitted factorial effects that were discussed in the previous module, in Module 44. The basic notion is that before one bases serious real-world decisions upon things like A main effects, B main effects, and AB two-factor interactions, one needs some level of confidence that what is computed is more than just some kind of estimate of noise, that there's clearly something going on, that an A main effect or a B main effect that one computes is more than just background chatter. The way we're going to approach this is to make use of the material from Module 42 that had to do with L's and L hats and making confidence limits for L's based on L hats, and here's how we're going to get that into play. We're going to notice that in two-way situations that every main effect and two-factor interaction really is an L hat. It's a linear combination of cell means. So for example, in a 2x3 factorial study, like the glass phosphor study, the main effect of factor B at level 2 is a column average for the second column minus a grand average y bar. That means it is an average of 2 y bars minus an average of 6 y bars. If one then assembles coefficients, what one ends up with is some coefficient times the y bar for the upper left cell, another coefficient for a y bar on the first row in the second column, another coefficient times y bar on the first row in the third column, and so on. One winds up with coefficients times y bars. One winds up with an L hat. That means that these fitted effects are L hats. That means that they are estimates of corresponding linear combinations of population or theoretical effects that are the corresponding L's. One could think of taking this and replacing every y bar with a corresponding mu, this, and replacing every y bar with a corresponding mu, and that would define a theoretical effect of phosphor 2. The approach then is to say that the plus or minus parts of the confidence limits for the theoretical linear combinations serve as margins of errors to attach the L hats. What that boils down to is that one has fitted effects from Module 44 and margins of error. Margins of error being t-values times pooled s's times a square root of what is a sum of squared coefficients over sample sizes. Those squared coefficients over sample sizes added up, if we just knew what they were, we would know how to basically hedge AIs and BJs and ABIJs. Turns out that there are fairly simple and calculation formulas for what goes underneath that square root, at least in the case where all the sample sizes are some fixed value m. That is in the so-called balanced data case. And those formulas are collected in Table 6.5 of Vardaman and Job. The more complicated formulas that are necessary when data are not balanced are collected in Table 6.6 of Vardaman and Job. In this particular module, we're going to concentrate on the simpler balanced data case. So, for example, the interaction of factor A at level I with factor B at level J that we have symbolized as ABIJ has a corresponding theoretical counterpart. The first is an L hat, the theoretical counterpart is an L. And to make confidence limits for this theoretical L, one takes L hat and takes plus or minus t value s over square root of a sum of coefficients squared over sample sizes. And in this case, that is a fairly simple form. I can take the number of rows minus 1 times the number of columns minus 1, put it over the common cell sample size times number of rows times number of columns. There are similarly simple formulas for margins of error for A main effects, for B main effects. They are these. In this case, it's number of rows minus 1 over common cell sample size times number of rows times number of columns. And perhaps what is more useful than the A's individually, if I want to talk about a difference in A's, a difference between glass 1 and glass 2 main effects, then the sum of coefficient squared over sample sizes is even simpler. It's simply 2 over the common cell sample size times the number of columns. And if I want to talk about difference in B's, it's 2 over m times I. So, for example, in the glass phosphor study, we had I of 2, J of 3, common sample size was 3. So if one wanted to attach a margin of error to any one of the interactions, a way to do that would be to take a t-value times the pooled s times I minus 1 times j minus 1 over m times I times j. And in this particular case, that works out to be the square root of a ninth. The t-value is 2.179. If we're working on 95% confidence, that number is the same number that was used when we were ignoring the two-way structure of the glass phosphor data, and there is the pooled S. That is associated with every ABIJ is a margin of error of about 6. If you'll remember, those ABIJs were numbers like plus or minus 2.22 or plus or minus 1.11. They're known only to within about 6 microamps. That is, confidence limits based on those fitted effects include 0, positive values, negative values. The take-home message then is that I don't even know the sign of those things, and that says that the real interactions, the real lack of parallelism is potentially 0. That is, any lack of parallelism that is seen on the interaction plots is is not only small in comparison to the size of the main effects, it's down in the noise range. We don't even know for certain that there is lack of parallelism. And that's pretty much what's conveyed by this picture. That's not too surprising. That by the time you take into account these error bars around the sample averages, there's no definitive evidence that there's lack of parallelism on the real means that stand behind that set of sample means. If one wanted to apply a margin of error to the difference between fitted factor A main effects, that is, take, for example, A2 minus A1. A2 minus A1 is minus 54.44. We're talking about basically the gap between the row average here and the row average there. It's a pretty good sized gap. One could say, well, that is known somehow to within this margin of error. There's a t-value, a pooled S, and then 2 over the cell sample size, which is 3, times the number of columns, which is 3. So that is about 8.6 microamps. And the point here then is, since that difference in absolute value is bigger than the margin of error, there's a clear difference between glass 1 and glass 2 main effects. And again, that seems more or less obvious from the plot. If one wanted to compare B main effects, any difference in fitted B main effects is going to have a standard error turned in by the time multiplied by a t-value, a margin of error, that is t-value pooled S times the square root of 2 over 3, which is the cell sample size times the number of rows. It's going to be about 10.25. And if you'll remember, differences between the B's, the fitted B main effects are a couple of them are will exceed 10.5, but that is difference between the phosphor 2 main effects, and 1 and 3 will exceed this, but the difference between 1 and 3 is not going to beat 10.5. The virtue of having these measures of main effects and interactions and learning how to attach these margins of error is that we have ways to quantify what's going on in a scenario like this that will be able to extend to situations where there are more than 2 factors and one can't make this kind of nice picture that we've relied so heavily on in the glass phosphor study. And so subsequent modules, we're going to begin to consider 3 and a higher way factorials, 3-factor studies, 4-factor studies, and so on.